Wow, it smells great, but I hope it tastes good too.
I hope so too. How many carrots was it again?
Sure I can. What kind of music
No,
would you like to listen to?
no,
I can
no
really
music.
recommend a new Beatles
Right,
collection.
no music.
Have you ever heard of the Beatles?
Voice control interfaces have changed profoundly the way we interact with technology. However, they are bound to fail in the interactions with humans. These failures can be critical because they require costly human intervention and can cause users to lose trust. Most research approaches start with the assumption of flawless interactions. However, as conversation is the main interface, visual feedback may not always be available. Users typically expect an interaction in an orderly fashion. In this paper, we use a set of failures informed by taxonomies of failures in previous studies in HRI. The induced failures represent typical robot malfunctions that have been reported in human-robot interactions. They were either task-oriented, such as giving incorrect guidance, or failures that violate social protocols of interaction. All failures have the consequence of delaying users in completing a task. The failures we used were the following. In this failure, the system simulates losing user engagement and restarts the interaction. After the failure has occurred, the robot becomes responsive and continues the guidance. And sample user response to the failure follows.
We have already started. We have already started.
In this failure, the robot time speeds improperly by producing an incomplete instruction, and after a short delay, continues its utterance.
Next, take the
Take the one.
mushroom and add it.
In this failure, the robot simulates lack of user speech input by not responding for 20 seconds.
I'm done. What is next? I'm done. I'm done. What is next? Oh, this is not working. I'm done.
Take 1 spoon of red cabbage and put it in the spring roll.
In this failure, the robot repeats a previous statement by asking the user to perform again the previous instruction. And finally, in this failure, the robot produces an erroneous instruction by asking the user to pick up a non-existing object. Using the failures above, we asked human users in this corpus to engage in a referential communication task. Users were instructed how to cook spring rolls by 2 robots. Spring roll recipes were broken down to interaction segments and used for instructions. The recipes were non-trivial, so users had to interact with the robots to successfully complete the task. Interactions were segmented into dialogue acts, and the robots would reply to clarification questions from human users. Users were not instructed on dialogue options, but had to interact with the agents to find out. Participants were led to believe that robots were autonomous. However, to dismiss technical problems, we used a human operator. There is a long-standing effort in bringing human likeness to robots, but how robot embodiment affect users' behavioral responses to failures remains largely unexplored. Smart speakers and human-like robot embodiments, for example, differ in interactional affordances, from transactional to relational interactions. While robot embodiment has shown to typically positively impact human-robot interactions, it remains to be explored if this effect persists when the robot fails. The robots we used were the following. An Amazon Echo device that used voice as an only output modality, and a Fairhat robotic head for the human-like robot embodiment. Time-critical situations are difficult to convincingly simulate in the lab. As such, most studies have focused on robot failures where little is at stake. In this work, we introduced a time pressure to half of the participants using a timer on the screen. We expected that under time pressure, the same failures would have a higher severity on the task. We therefore separated failures to low severity failures, little to no consequence of the failure, versus high severity, more severe consequence of the failure, respectively. In a user study with 44 participants, we investigated the impact of these 2 different factors. One is robot embodiment, and the other one is failure severity. Using this video corpus, we define 2 types of states in the interaction. The first is a no-failure state, where the user is working on a robot instruction. And the other state is a failure state, in which the robot has either not responded or provided an erroneous instruction. To assess behavioral responses, first, we ask human annotators to estimate user affective states in responses to failures. And then, we train a random forest classifier to detect whether a robot failure has occurred. Human annotators estimated whether a conversational failure occurred looking at short video segments of user responses. These were 2 in-lab annotators and 192 online annotators from a crowdsourcing platform. They watched the videos from the perspective of the robot and coded the following items. Does the person look confused? Does the person look uncertain? Does the person look distressed? And how engaged is the person with the robot? Then we attempt to predict if a failure has occurred in the same video segments using multimodal input from human users. Behavior is represented in gaze and speech features as well as user actions. For example, more body movement shows subjects are working on the instructed task, where lack of movement shows hesitation. We found statistical differences in user engagement with the robot. Specifically, participants appear to be more engaged with the robot when it failed. Failures need to be resolved before moving on to the task. The main findings are the following. Annotators were better at detecting states of no failures than failures. When no speech features are presented to annotators, it is much harder to detect states of confusion caused by robot failures. This further indicates the importance of speech and context features in failure detection. We also observed that the classifier performed better at detecting no failures than failures. There was, however, no significant difference among robot embodiment in how well the classifier performed. However, getting a closer look at the models and what features contribute to failure detection, we found the following. In most conditions, head movement appears to be the most important feature. This we define as an embodied contribution to the ground and is expected to work well in task-oriented dialogues. We, however, observed that gaze features are more prominent when the human-like robot is present, while there is a preference for speech features in interactions with the smart speaker. We saw a clear separation of the failure classes in the case of the human-like robot embodiment when looking at the participant's gaze. Similarly, a clear separation appeared in the speech features across classes with the smart speaker embodiment. These subtle differences in features indicate that the models for each embodiment are inherently different. The models in each embodiment work equally well, however, different features are activated when the smart speaker or the human-like robot attempt to resolve failures.
Why are these findings important? Robot embodiment affects how users will interact with a robot, and therefore also how they respond to failures. How the robot looks like is important regarding what features it should pay attention to when trying to resolve conversational failures with users. This is important for failure detection mechanisms, which may need to consider the robot's physical design in their failure detection model.